compute the adjugate of the given matrix and then use it to find the inverse. So the first thing that we need to do here is find the adjugate. So we need to find the matrix of cofactors of A. And since A is a 3 by 3, our matrix of cofactors will also be a 3 by 3. So we're going to need to use that cofactor formula to find each one of these entries. And then we'll take the transpose of it to attain the adjugate. So here we go. And again, keep in mind that for the ith jth entry, we know that the cofactor C is defined as -1 to the I plus j multiplied by the determinant of the submatrix in the attained by eliminating the ith row and jth column. So here we go. The first cofactor, or the cofactor in the first row, first column, is -1 to the 1 plus 1 is 2, multiplied by the determinant of the submatrix, which will be 2, 0, 4, 2. So this leaves us with 1 multiplied by 4 minus 0, which is 4. So then we have the cofactor in the first row, second column, which is -1 cubed multiplied by the determinant of the submatrix -3, 0, minus 1, 2. So this will be -1 multiplied by -6 minus 0, which leaves us with positive 6. We have the cofactor in the first row, third column. So we have -1 to the fourth multiplied by the determinant of the submatrix -3, 2, -1, 4. So this is positive 1 multiplied by -12 minus a minus 2 or plus 2 or minus 10. So now we need the cofactor in the second row, first column. So that's -1 cubed multiplied by the determinant of the submatrix 0, 0, 4, 2. So this will leave us with 0. And you need a little more room. We have the cofactor in the second row, second column, which is -1 to the 2 plus 2 is 4, multiplied by the determinant of the submatrix. And again, I'm obtaining all of these submatrices by eliminating the adjacent row and column. So this here, we are eliminating the adjacent row and column of entry 2. So this leaves us with the submatrix 4, 0, -1, 2. So I have positive 1 multiplied by 8 minus 0, which is just 8. We have the cofactor in the second row, third column, which is -1 to the fifth, multiplied by the determinant of the submatrix 4, 0, -1, 4. So this will be -1 multiplied by 16 minus 0, which is -16. And I'm going to bring matrix A down here so that we can give ourselves more room and still see matrix A. Oh, we need all our cofactors. All right, last row. So we have the cofactor in the third row, first column, is -1 to the fourth multiplied by the determinant of the submatrix 0, 0, 2, 0, which is just 0. We have the cofactor in the third row, second column, which is -1 to the fifth multiplied by the determinant of the submatrix 4, 0, -3, 0, which is also 0. Woohoo! And last but not least, we have the cofactor in the third row, third column, which is -1 to the sixth multiplied by the determinant of the submatrix 4, 0, -3, 2, and this is 8. Phew! So our matrix of cofactors, C, is going to be 4. So our first row is 4, 6, -10. Second row is 0, 8,-16. Third row is 0, 0, 8. And to attain the adjugate, we take the transpose of this matrix. So interchanging the rows and columns, we are left with a first column of 4, 6, negative 10. Our second column is 0, 8, negative 16. And our last column, our third column, is 0, 0, 8. And so this the transpose of the matrix of cofactors is the adjugate of matrix A. So now that we have the adjugate of matrix A, we are ready to find the inverse. So by the inverse formula, we know that this is 1 over the determinant of A multiplied by the adjugate of A. So we have the adjugate of A, and we now need to find the determinant. And I'd like to introduce an alternative method here. So there's two ways to find the determinant of A. We have our familiar way. We could use the definition, which is fine in this case because we have a 3 by 3 matrix with lots of zeros, so it would be cute and quick, but we won't always have such nice matrices. So the alternative that I want to introduce to you is as follows. So we could also find the determinant of A by computing the following product. We can left-hand multiply matrix A by its adjugate, which will produce a scalar multiple of the identity matrix in whatever dimension you're considering. And this is such that K is a scalar, which is, this K value is the determinant of matrix A. So we can find the determinant of A either using the definition or using this formula here, which again is going to be particularly useful when we have much larger matrices. So I'm going to use case 2 here, and we can confirm it with our definition. So to find the determinant of A, we need to take the product of the adjugate of matrix A with our given matrix A. So this is going to be 4, 6, negative 10, 0, 8, negative 16, 0, 0, 8, and this is multiplied by the given matrix, which was 4, minus 3, minus 1, 0, 2, 4, 0, 0, 2. And so to compute this, we will use the row column rule. So starting with our first row, we have 16 plus 0 plus 0. We then have 0 plus 0 plus 0. And then last but not least, we have 0 plus 0 plus 0. So moving on to our second row of the adjugate of A, we're going to have 6 times 4 gives us 24. Then we have minus 24 plus 0. Moving to the second column, we have 0 plus 16 plus 0. And the third column, we have 0 plus 0 plus 0. So now taking the third column of the the third row of the adjugate of A, we have negative 40 plus 48 minus 8. We then have 0 minus 32 plus 32. And last but not least, we have 0 plus 0 plus 16. And simplifying here, in our first row, we have 16, 0, 0. In our second row, we have 0, 16, 0. And in our third row, we have 0, 0, 16. So we can see a scalar multiple of 16 here, multiplied by the identity matrix in 3 dimensions. And so therefore, the determinant of matrix A is that scalar multiple 16. And again, we can confirm this using the definition of the determinant. And so I will leave that up to you. So now that we have the determinant and we have the adjugate of A, we are ready to find the inverse. So we know that A inverse is 1 by the determinant of A multiplied by the adjugate of matrix A, that transpose of the matrix of cofactors. So I have 1 by 16 multiplied by the matrix 4, 6, negative 10, 0, 8, negative 16, 0, 0, 8. And of course, we want to simplify this. So if we distribute our 1/16 through, this is going to leave us with a beautiful final answer of 1/4, 0, 0. We then have 3/8, 1/2, 0. And then in our last row, we have negative 5/8, negative 1, 1/2. And so we have found the inverse of our given 3 by 3 matrix using the inverse formula by Cramer's rule.